So thank you, everybody, for coming to this, the penultimate session of Hadoop Summit San Jose. So thank you for making it this far, and thank you for sticking around for our session. So, and if you stay to the end, you can win this beautiful Amazon Echo. If you don't already have a ticket, then put your hand up, and there's a couple of reels of tickets coming around, and you'll get yours. So with that, we'll get started. Ingest and stream processing. What will you choose? So Anand, why don't you introduce yourself?
Sure. My name is Anand Iyer. I'm a senior product manager at Cloudera, focusing on the Apache Spark ecosystem and tools for data ingestion. Before joining Cloudera, I've been at Cloudera for about 18 months now. And before joining that, I worked as an engineer at LinkedIn working on feed relevance. The original speaker was going to be Ted Malaska. He unfortunately couldn't join us because he had other commitments. Now, Ted is an expert in this field, so I do have some big shoes to fill.
All right. And I'm Pat Patterson. I'm the community champion at Streamsets. It's a role I've held now for just coming up to 3 months. Before that, I was a developer evangelist at Salesforce. So I've actually been learning this whole big data technology, and I'm pretty much up to speed now, I think, as far as ingest goes. You can follow Anand on Twitter at Lost on Logic, and you can feed my personality cult at Metadaddy. It's the only reason I do these things. So the way this is going to work, Anand's going to take you through what we mean by ingest and the particular problems and how streaming technology works with that. And then I'll actually show you an example in action. So Anand, take it away.
Thank you. So there are many open source tools out there for streaming data ingestion and real-time stream processing. So what we're going to do is we're going to give an overview of the popular tools out there. We're going to highlight their strengths, their weaknesses, their unique features. And the goal is to help you decide the right tool to pick when you're building your streaming architecture. This is a very pragmatic talk. It's just aimed towards helping people pick the right tool. We're not going to spend too much time going under the hood, so to speak. We're not actually going to look at how some of these tools work, like their architecture, and what are some of the tricks they apply for the capabilities they provide. So it's more geared towards an end user who wants to build pipelines and wants to pick the right tool for the job. The second thing I want to mention is we're sharing our opinions. These are opinions we've formed by working with customers, hundreds of customers that have built streaming, ingestion, and stream processing pipelines. But at the end of the day, they are our opinions. This is not based on some rigorous scientific study. And as such, you may disagree with some of our opinions, which is fine, which is the beauty of being part of an open source ecosystem and participating in a summit. So if there are disagreements between our opinions and yours, they're not meant to offend. They are opinions, and take them as such. So quick agenda, we will start by talking about ingestion, just the tools for getting data into your platform in a streaming fashion. Then we'll talk about how to perform simple, low millisecond basic processing of events as they stream in. Then we'll talk about, or rather the meat of the presentation, a lot of time will be spent talking about complex systems for real-time stream processing, systems where you actually have a topology or DAG of operations. Then we'll talk about abstractions for stream processing, and then I'll give it over to Pat to actually present Streamsets, which is a wonderful UI-based abstraction to build these pipelines. So with that, let's dive in. Now, if you look at a streaming pipeline, it usually consists of 4 components, broadly speaking. You start with your producers. That's the source of the data. From the producers, the data will go to Kafka. Kafka, at this point, has established itself as the leading streaming data channel or high-throughput message bus, so to speak. And there is near unanimous agreement that for big data streaming, Kafka is what you want to use. It has tremendous throughput, low latency, flexibility. It lets you replay data, and also different consumers of the data can be consuming at different rates at different points of time. So because of all these reasons and the fact that it actually runs on commodity systems, it has essentially established itself as the standard. So for Box 2, for the streaming data channel, Kafka is the tool to use. There is no debate or discussion there, so we actually won't be talking much about that. Bulk of the time will actually be spent in talking about the streaming data engine, which is where, as the events come in, you might do some processing. And of course, lastly, it's the destination, right? At the end of the day, you have some application. There's an end user that's going to interact with that application through some UI. It could be a web or mobile UI, or it could be some alerting system. And there has to be some way for that application to serve that data. So often the destinations are serving systems. And if you're doing just mere ingestion of the data, you're not modifying the data as it's being ingested, the third box is irrelevant. But often people will do some processing of the data as it streams in. And for each of these, actually broadly speaking, I'm going to make an assumption that we're only interested in building pipelines where you do not want data loss. Just for simplicity of the rest of the flow, let's just assume that we don't want any data loss. So all our pipelines, the pipelines we're going to talk about, will give you zero data loss. And if you want zero data loss, there are certain considerations or a few things you have to think about for each of these boxes in terms of the delivery semantics. So let's start with the producer. Now, the producers are writing to Kafka. So the producer writes an event to Kafka. The event is received by Kafka. Kafka sends an acknowledgement, and that acknowledgement is lost because of, say, some network failure. Now, that producer has, to ensure zero data loss, the producer has to simply resend that data. There's no way around that. So from the producer to Kafka, if you want zero data loss, you will have what is called at least once semantics. And what that means is the data is written at least once, but that also means the same event could have been written more than once. And that's just how the producer to Kafka interaction is going to work. Now, within Kafka itself, Kafka is ordered and partitioned. Then from Kafka, the data goes to your stream processing engine. And different stream processing engines have different semantics. Some stream processing engines will, again, give you at least once semantics. And what that means is you have a cluster of machines processing these streams of data. Some machine or process failure is going to happen, at which point the data will simply be reconsumed and reprocessed. So if you're maintaining some aggregation, that means when you reprocess that data, if you're maintaining a count or an aggregation, that's going to be counted twice. And certain engines actually give you what is called exactly once semantics. And what that means is, despite the fact that there will be machine or process failure, and despite the fact that events will actually have to be replayed and reprocessed, the framework will ensure that the end result is as if those events were processed exactly once. But that is still within the processing engine. So for example, if the processing engine itself is maintaining some state or some counts, it'll make sure that there isn't any overcounting or unnecessary modification of that state. But again, when the data goes from your streaming engine to the destination, it's going from one system to the other. Again, whether you get exactly one semantics or not depends on the properties of your destination. It depends on whether that destination has the required constructs to ensure exactly one's semantics. So depending on the semantics you're OK with, if you do want exactly one semantics, you do have to think about it at each step of this pipeline. So let's start with the destinations. A popular destination for data, streaming data, is HDFS. If you're streaming data into HDFS continuously, then you will get at least one semantics. But if you're actually writing data to HDFS, HDFS is not going to be part of any real-time application, right? Once you write the data to HDFS, there's nothing real-time happening at that point. So you're probably often just better off doing a batch pull from Kafka using some system like Camus, doing a batch pull from Kafka and writing to HDFS. And if you're actually doing these batch pulls, you can guarantee exactly one's semantics. But then again, that may be moot because do remember, the producers cannot guarantee exactly one's semantics. Now, if you're writing to a system like Solr or Elasticsearch, In Solr or Elasticsearch, it's document-based. You're essentially putting documents in there, and then the documents have properties, and then you index the documents. So if you redundantly update a document or enter a document twice, because they're document-based, you essentially overwrite what's in there. So you do get exactly once semantics. And the same thing holds true with NoSQL stores. And actually, NoSQL stores are probably the most popular destination for a real-time streaming pipeline, because they're the fastest way of serving lots of data. So NoSQL stores, each record has a unique key. So again, if you double write for a key, it overwrites the existing values, so you do get exactly one semantics. However, a lot of NoSQL stores do have an increment operator. And if you invoke the increment operator, then of course, you will get double counting, so you won't get exactly one's semantics. Now, I do want to mention Kudu. Kudu, as my colleague Ted Malaska would say, Kudu is the love child of HDFS, HBase, and Kafka. It gives you fantastic scan performance, which is why it's similar to HDFS. It also gives you really good random access to data, like a NoSQL store. And some of the internal mechanics of how Kudu works are a little similar to Kafka. That's why we call it the love child of HDFS, HBase, and Kafka. So Kafka is increasingly becoming a popular destination for streaming data. And of course, one thing not called out here is, in certain cases, if you're doing something like fraud detection, where there are periodic events that have to be sent downstream from your stream processing engine, then you can actually write it back out to Kafka, and then from Kafka, you can have certain consumers. So those were the destinations. Now, if all you're doing is just simple, basic ingestion into the destination, all you want to do is get data into the destination, then for HDFS and for actually most of these systems, a popular tool is Flume. Flume has this ecosystem of connectors. They're called Flume syncs, and they're fairly easy to set up. So Flume syncs are a popular tool for just writing data if you don't want to write any additional code, getting the data from Kafka into the destination. Kafka Connect is part of the Kafka ecosystem. It's a newer tool for connecting Kafka with destinations. It works really well for HDFS. And of course, if you're writing to NoSQL stores or Solr or Elasticsearch, a lot of the streaming engines have inbuilt integrations. So that's just basic ingestion, nothing really terribly interesting so far. Now, from the destinations, I'm going to jump all the way to the beginning. Let's talk about producers, because once we're done with the destinations and producers, we'll actually spend a lot more time talking about the stream processing engines, which is the meat of the talk. So tricks with producers. Now, producers write data to Kafka, right? So clearly, you can have a system that uses Kafka's producer API to write the data into Kafka. But if you don't want to write code and you don't want to write code for all the time, you can actually use Flume's library of sources. So Flume has these connectors for popular types of data. It has connectors for if you're tailing logs. It has a REST-based endpoint. It has connectors for mainframes and so on and so forth. So if you're collecting data from these commonly used sources of data, you don't have to write code. You can use an existing Flume source. And the Flume source will write directly to Kafka. Now, exactly once processing semantics is something that I think over time, as we're building stream processing systems, it should become the norm. So you want to start thinking about that. And because the producer cannot avoid double writing data in certain cases, what you can do is for each event that is written, you associate a unique ID with that event. So even if the producer wrote an event with that unique ID, it didn't get an acknowledgement, so it has to rewrite. In Kafka, you ended up with two events, but both those events have the same unique ID. So when you're processing the data, you can do the required deduping. Again, it's probably not terribly new. I'm guessing this is common knowledge. Now, something else to think about if you're writing data to Kafka is that Kafka is partitioned. It has a bunch of partitions that are distributed over the brokers. And when consumers are consuming data, a single consumer will consume data from the same partition. Or rather, data from the same partition will end up at the same consumer. So if the data you have has some property by which you want to partition it, so for example, if you're consuming sensor data, you probably want to process all the data from the same sensor within the same consumer or within the same node or agent, because you're probably doing some aggregations and so forth. Or if you're processing user session data, you probably want all the events for that user session to go to the same node. in which case you probably want to partition it at the source. When you're writing to Kafka, use this partitioning key. And what that will give you is it'll save redundant shuffles down the line. Again, this is not a very important consideration. A lot of the stream processing engines, even if they do a redundant shuffle, it's not a big deal. But this just gives you, if you're aware of it, you can do partitioning up front. It'll give you a better, your system will run with a little bit more efficiency because you've avoided some redundant shuffle of the data. But if you are going to use a source ID, do remember that you want to make sure that isn't heavy skew. Because if most of the incoming data is going to have the same key, then you end up with one bloated partition that's going to affect performance. So that's something to be mindful of. All right, so now we're going to talk about the streaming engines. And let me just do a time check. I think we're doing good. So first, I want to talk about simple streaming processing. Simple. You want to keep simple things simple, right? And often all you're doing is you're consuming from Kafka. As each event comes in, you do some simple processing of that event. Actually, it need not be simple. You could invoke a machine learning model. It could be that sophisticated. But the key thing is, if you're going to look at each event in isolation, you're not doing any aggregations across different events. You're not maintaining any state. You look at each event, you do something, and send data downstream. If that's all you're doing, then Flume with interceptors. Interceptors are essentially little snippets of code which run within your Flume agents. You have a distributed set of Flume agents. They're reading from Kafka. They run the interceptor, send the data downstream. Kafka Connect is going to have a similar notion. That's actually work in progress right now. Will be available soon. So with that, you get very low latency. You get high throughput. You do not get exactly once processing semantics. You will get at least once. Events can be double processed. You also won't have any stateful processing and so forth, but often you don't need all this. So you can keep simple things simple. It's actually very trivially easy to deploy Flume with interceptors or Kafka Connect. May not sound cool, but often that's all you need. So keep simple things simple. Well, let's talk about Storm. Full credit to Storm. Storm is the first popular open source stream processing engine. It actually brought real-time stream processing back into the zeitgeist a few years back, and then since then it has spurred a lot of innovation in this field. So full credit to Storm for that. One of the advantages of Storm is you actually get to process data as it's coming in with complex topologies and so forth, so multi-hop processing as the data streams in, but you still get low latency. So with Storm, you can actually achieve latencies as low as 100 milliseconds or 50 milliseconds. And by latency, I'm talking about the amount of time that the event spends within the stream processing engine before you have the result for each corresponding event. But what you do, the compromise you make for getting that low latency is you get lower throughput. So Storm does have lower throughput as compared to some of the counterparts. The API is also a little minimal. You get at least one processing semantics. You don't get exactly once processing semantics. You also don't have any stateful operations. And you get fairly simple primitives. You get spouts and bolts. And our experience, and this is just our opinion based on what we've heard, Storm is a little hard to deploy and monitor. Now, if you want exactly once processing semantics with Storm, and you want stateful operations and so forth, there is a project called Trident, which is built on top of Storm, which you can use. With Trident, you get exactly once semantics. It has a micro-batch architecture. So Trident and Spark Streaming both have a micro-batch architecture. And again, just a brief description of micro-batch architecture. To put it, I'm oversimplifying it, but to put it simply, you read a bunch of data, you batch together a bunch of data, you're batching together a bunch of data for, say, a few hundred milliseconds, and then you process it, and then you do that for the next batch, and so on and so forth. So you do get that with Trident. Of course, if you're doing micro-batching, the latencies go up. So with Trident, the latencies will be upwards of, say, half a second. But if you are going to go with a micro-batch-based architecture, then if you compare Trident and Spark Streaming is the engine we would recommend. It has a much nicer API, and we'll talk about it more in the next slide. But if you are going to use Trident, and these days, because all of these systems run on Yarn, you can actually have one pipeline running with Storm and another pipeline that's using Spark Streaming. So there's no real motivation, according to us, to use Trident. And the last piece is Storm at this point, the community is dwindling. Storm was born at a firm that was acquired by Twitter. So Twitter was where Storm was primarily, for the most part, run at scale and developed. And about 2 years back, Twitter decided to rewrite Storm. They have their own new system called Heron. They have actually blogged about it. They've published a paper. So the fact that the place where Storm was born and really developed has moved away from Storm is a sign, and the community is dwindling. So we actually believe Storm is close to being legacy at this point. But that, again, that is our opinion based on conversations with customers. Cool, so let's talk about Spark Streaming. Spark Streaming at this point is the juggernaut. It is the most widely adopted stream processing engine. It gives you really high throughput. Arguably, it has the best API for stream processing. It's an API with simple constructs for sliding windows of time, simple constructs for maintaining in-memory state. You can also do a lot of operations now thanks to the Spark SQL initiative by just embedding SQL statements or using SQL-like syntax. And actually, I want to just give you a preview for an upcoming major improvement in Spark Streaming called structured streaming, where you can now start viewing your streams of data as continuous data frames. And a data frame is analogous to a table. So you view it as a continuous data frame, and you use SQL to process your stream processing job. That's just a preview. It's not available yet, so I'm not going to spend too much time talking about that. But it's fairly compelling. But as I mentioned before, Spark Streaming does run on a microbatch architecture. So what that means is it cannot achieve latencies as low as Storm or some of the other engines out there. That being said, with Spark Streaming, it's fairly easy to achieve sub-second latencies. In fact, the microbatch sizes can be as low as 250 milliseconds. So 250 millisecond microbatches can be achieved without difficulty. Of course, if you go lower than 250 milliseconds, now you'll actually have to do a lot of hyper tuning and so on and so forth. But up to 250 milliseconds, no problem. And if you're going with 250 millisecond microbatches, then you effectively get half-second latency. One of the strong points for Spark Streaming is it has a vibrant community because it's part of the Spark ecosystem, and the Spark ecosystem, as most of you know, is incredibly vibrant. It gets to leverage a lot of the developments in the overall community, and a great example is MLlib. MLlib has established itself as the leading open source distributed machine learning and statistical analysis toolkit out there. And MLlib can be seamlessly invoked within Spark Streaming. In fact, in MLlib, there are a lot of algorithms that are tailored for doing machine learning on streams. And a good example is streaming k-means, where you're clustering data, but as the data streams by, you're dynamically adjusting the clusters. So that's fairly compelling. So if you're actually going to do machine learning in the context of streaming, Spark Streaming is kind of the slam dunk for that. Now let's talk about Flink. Flink is compelling. If I had a funny T-shirt to distribute for Flink, the T-shirt would say, "I'm better than Spark. Why doesn't anyone use me?" So arguably, if you look at the architecture, the underlying architecture, some would say arguably Flink has the best architecture for real-time stream processing. It gives you an API similar to the Spark Streaming API you have in-memory state and so on and so forth, exactly once processing semantics. But it also gives you lower latencies than what Spark Streaming can provide. With Flink, latencies lower than 200 milliseconds are fairly easy to achieve. It has this technique called asynchronous barrier snapshotting, which I'll give a preview to how asynchronous barrier snapshotting works. So Flink is fairly compelling, but the reality is that there aren't as many known production instances out there for Flink as with Spark Streaming. So what that means is if you're going to use Flink, you just be careful that you might hit more bugs than you might with Spark Streaming. The community is a lot smaller than Spark Streaming, so you don't get the ancillary benefits of a SQL-like syntax or machine learning and so on and so forth. But a quick show of hands, I'm curious to know how many Flink users we have in the audience. Well, that's interesting. There are usually a few Flink users, but I don't see any hands go up. It's an interesting data point. But yeah, Flink is compelling from a technical perspective. Now, I do want to talk about how asynchronous barrier snapshotting works very briefly, and the reason being, with microbatching, it is fairly intuitive to understand where checkpointing or snapshotting might occur. And again, checkpointing or snapshotting, if you're going to do stateful operations or if you want exactly one semantics, it's a fact of life. You have to do some checkpointing because machines will fail. You need to know where to pick up, right? So that has to be done. And with microbatching, it's rather intuitive. This checkpointing or whatever happens at the microbatch boundaries. So when does Flink do it if it doesn't have a microbatch architecture? So what Flink has is It does snapshots, and there are snapshots that are ordered, right? So you have snapshot 1, snapshot 2, so on and so forth, snapshot n plus 1. For each of these snapshots, it introduces at the source what are called snapshot barriers. And these barriers move with the data. They're streaming with the data. Now, Flink it allows processing via complex DAGs, right? You're authoring, you don't have to construct your DAGs with low-order primitives. You do get a higher-level API, but at the end of the day, it breaks down into a DAG, which has operators, right? So at each operator, it waits for the snapshot barriers for each stream that flows into the operator. And as soon as it gets all those snapshot barriers, it will create its own snapshot barrier and send it downstream. And once the end of the DAG, at the end of the DAG, the results are written out to, say, the final destination, then that final sync, when it has done processing the snapshot barrier, it will let some coordinating system know that all the barriers for a particular snapshot have passed, which means that snapshot can be considered to be committed, for lack of a better word. And also, when all the barriers for a given operator corresponding to a given snapshot, so let's say the next snapshot is snapshot n, when all those barriers for snapshot n reach a particular operator, it also kicks off asynchronously some checkpointing of state information. So that is a very brief and quick summary of how asynchronous barrier snapshotting works, simply because that question almost always comes up because it's not intuitive how it does snapshotting or when it does so. And again, in the interest of time, I'm just going to run through Kafka Streams. The reality with Kafka Streams is it's the new kid on the block, very new, I think less than 2 months old at this point. So time will tell. It is compelling. Let's see how it pans out. There aren't that many known production instances out there. It does give you low latency. It does give you high throughput. It does not give you exactly once processing, but it does allow stateful processing. Now, the thing to remember with Kafka Streams is Kafka Streams and the Kafka brokers themselves are separate. Your Kafka Stream nodes or processes are running separately from the broker machines. And also, Kafka Streams uses Kafka itself for all intermediate data, because after all, there is a DAG, right? So a lot of intermediate data. There's also checkpointing of data that needs to be done. It uses Kafka for all of that. So if you're going to use Kafka Streams, you better be incredibly comfortable administering a Kafka cluster. Kafka is by far the best solution out there as a channel of streaming data, but it's not zero overhead. If you're pumping a ton of data through a Kafka cluster, there are some administrative overheads. So if your streaming data is already high volume, and now you use Kafka Streams, that's actually going to grow the volume of data flowing through that Kafka cluster because of all that intermediate data that's going to go from the Kafka Stream processes or nodes back to the Kafka cluster and so on and so forth. So unless you are very comfortable with administering a Kafka cluster, Kafka Streams is probably not something we'd recommend, and also it is very new. Now, clearly, a ton of choice out there, right? So it's very compelling to have an abstraction. You want to future-proof yourself. You want to write to an abstraction so that as technologies come and go, you don't have to rewrite your application each time. You can just swap out the underlying implementation, and that's why abstractions are compelling. SQL, of course, is the most popular abstraction that has stood the test of time. A lot of the streaming engines are starting to provide SQL-like abstractions to author jobs. So what that means is when you swap from one engine to the other, it's not zero effort, but it's minimal effort because most of it is done through common SQL-like syntax. Google has open sourced this project called Beam, which is a programmatic abstraction. Now, again, it's new, so let's see how it pans out. But with programmatic abstractions, it's a little tricky because the programmatic abstraction becomes redundant fairly fast because the underlying engines will add the required features. So programmatic abstractions tend not to be as compelling because it's geared towards a developer audience, and often a developer audience just wants to work with the underlying API for the underlying system. And lastly, the most compelling abstraction is a UI-based abstraction. So with a UI-based abstraction, simple things become incredibly simple. And also, you don't have to be a coder, so you open up the audience for real-time stream processing. You open it up to a very broad audience. In fact, you can have analysts and even, at some point, direct business end users using these UI-based abstractions to build streaming pipelines. And with that, I want to give it over to Pat to talk about Streamsets, which is an open source, very compelling UI-based abstraction.
All right, thank you very much. So thank you, Anand. So as Anand mentioned, Streamsets is open source. It's the name of the product is Streamsets Data Collector, so Apache 2 license. And the name of the company is also Streamsets. And I'm not going to spend much time on this slide. You can go to our website. You can go to Crunchbase for all of this information. But very briefly, Streamsets was founded about 2 years ago by veterans from Informatica and Cloudera. So they brought together this kind of traditional ETL data processing background with the requirements of big data. And the two founders kind of realized that there weren't really many tools that addressed the problems that we see when we're trying to ingest data. So in the next 9.5 minutes, I'll show you what we built on top of Spark Streaming. So the app runs either standalone, which I'm doing because this is just my laptop, or Spark Streaming, or as MapReduce. So the use case that I wanted to solve with Streamsets when I first joined the company, in fact, San Francisco publishes public data for city lots. So this is a really nice test data set. An engineer in Germany turned the shapefile format, some GIS format, into JSON, and it's a great JSON data set. It's 189 megabytes. There's over 200,000 records. Individual JSON objects in the list can be over 500K. So really, really, really good test data set. And it includes, in each record, it has some address information, so from and to street, because a property can span more than one street number. The street name, the street type, so here it's 106 Midcrest Way, bunch of other metadata, or other data. And then what's really interesting is that it has the coordinates for the boundary of the lot, okay? So these are the map coordinates for going around the boundary. And this is why some of these records are so big. Could you imagine, like, properties can have a very, very convoluted boundaries. So we're going to ingest these records. And the problem that I set for myself was, what's the biggest property in San Francisco? Because the data's there, the coordinates for the boundaries are there. So I'll build a pipeline, and I'm going to be using Kafka as my source. I'm just going to pump records through Kafka, and I'm going to put the data into Kudu, which is then going to do my analysis. So let's get started. So I'm going to want a Kafka Consumer. So this is my Streamsets UI, and I'm basically just building the configuration here for my system. So Kafka, I'm going to want to ingest JSON records. Need to get the topic name right, or it's a very boring demo, because nothing ever arrives. And then, OK, that looks good. And then on JSON, these are huge, so I'm going to want to buffer up to 512K of JSON data. Now, there are a whole bunch of processors that I could add to my pipeline. I've read in the data from Kafka. I could combine fields. I could do simple operations like string operations without writing any code. But this boundary calculation, this area calculation rather from the boundary, is a little bit more than I'm going to be able to manage with those. So I can actually drop in some JavaScript. So I'm not going to type in the JavaScript in front of you. You'll be relieved to know. So it's a standard calculation just to walk around those coordinates, accumulating the area there. And then I basically flatten out the structure of the record, set the area, use the first coordinate as the overall latitude and longitude. So I'm going to copy that in, paste it in here. And a really nice thing about Streamsets is that it's essentially a pipeline IDE. So I get the chance right now, even though I have not set up a destination or anywhere for my data to go, I can do a preview. So if I set my data going, so bear with me. It's my test data source. So if I run the preview now, what I should be able to see is that I've got records coming out of my Kafka, and they are, they have this format that I'm expecting, and I can see them being processed here. So this first record, it's pulling out an area, and everything looks to be okay. It's detected an error, but if I click on that, I rather could just go down and find it. There it is. So it seems like one of my records isn't quite right. This geometry is null rather than having some profiles. Maybe I've got some dirty data, but it's picked that up for me. Okay, so I've calculated my area. I want to send the data into Apache Kudu. So just drag that down there. And for Kudu, I'm going to need to say that it's living on my laptop here at 7051. Again, the table's just the same, city lots. I don't need to do any mapping because I've carefully made sure that my column names are the same as my JSON property names, so I don't have to bore you with putting loads of stuff in there. So that should be good. And just because Kafka is lots of fun and a great way to connect up different systems, I'm going to drop in a second destination. So hook those up, tidy things up, and this Kafka is going to go to 0.9 as well. And let's see, we're going to write to city lots 2 as the topic. And we need to write JSON data. All right, so what we can do is let's just restart our data source, and we can start processing records. So fingers crossed, our little histogram underneath. Here we go. So I'm actually generating records just about one every half second, just so that we can get a feel for the data flowing through the pipeline. And what we can see is data's flowing. We can see these errors. There's a few of these with a null value. Maybe we need to just go back and fix the JavaScript. Maybe properties should have no boundary. But we can also interestingly see that some of the data here that's hitting Kudu actually has blank from street and to street. So you probably want to investigate that a little bit, but we're getting the error message back from Kudu because that's the primary key. If we go over and have a look at Kudu, then this is my schema. So again, just pretty much mapping in the JSON, but I could be munging it around a little bit more. And let's see how many records. So only 129 records so far, but straight away, we can do like the really obvious SQL query, select order by area, descending limit 10. So that gives us the top 10 of the properties so far. I mean, obviously, I could set this loose on the whole file, and it takes about 10 seconds, but that's not really as interesting because what we can show here is the ability of Kudu to, like we're writing to the table and doing queries all at the same time. It's a really nice database to use for this kind of interactive analysis. All right, so very quickly, the more astute among you are wondering, why did I drag that second Kafka producer on? Kafka is a really nice way of loosely coupling applications. And what I did was I wrote a Kafka Consumer as a Minecraft plugin. So what I'm doing here is I'm building a three-dimensional histogram of the city of San Francisco. And we actually get taller columns downtown where it's more densely populated with small blocks. And then green areas over there, like the Presidio, that don't get any blocks landing with them. So a bit of fun. But we get to see the data actually arriving in our map of San Francisco as we process it. Okay. All right. So I think we've got about a minute or two for questions. So there you go. Streamsets, ingesting from Kafka, writing to Kudu, doing that non-trivial area calculation, via a JavaScript processor, and also sliding it over to Kafka and, for visualization in my favorite visualization tool. And we've got about, we'll hang around in the corridor outside. We've got time for just a couple of questions.
We also have the raffle.
Oh, and we have the raffle. All right. One question and then the raffle. Shoot.
You mentioned it supports Spark streaming.
Yep.
Plans on supporting any other?
Well, that's a nice, yeah, and that's a great question. So we support Spark streaming. Also, we can run standalone or with MapReduce. Are there any plans for supporting other engines? That's the great thing with having an abstraction. If another engine comes along and takes the market by storm, that's probably not the right word to use. Takes the market. Yeah, absolutely. We could look at moving across onto that. But yeah, it's an abstraction that could be applied to different engines for sure. All right, so quick raffle. Where's the raffle here? Oh, one more question. Okay.
Regarding the first part of the presentation, I was just curious why did you consider Apache Apex at all?
Apache Apex. Honestly, it was the least popular amongst the open source tools out there. But the reality is we just didn't know enough about it to share an opinion. So that's the reality. It is the least popular, and in terms of number of known production installations, it lags behind the other engines, and we just didn't know enough to have an opinion on it.
All right, and who's going to win this marvelous Amazon Echo?
And has everyone received a ticket? No?
Oh.
In that case.
I think people are taking 2 tickets to increase their odds.
Oh, there's something rampaging across the Presidio there. It's like a slime. I can't remember what it's called. Oh, it's gone.
Yes, I am.
So are Minecraft apps written in Java, or does it have its own? Awesome.
We're all set?
Yeah.
All right. For the winner.
Has a
Back to the owners.
All right.
Oh, cool. All right, the ticket number is, drum roll, please. That's 1826992. I'll repeat that. It's 1826992. Who is the lucky winner?
Is it? Do you have it?
Oh, sweet. Nice.
Let's have a look. 1826992.
We have a winner.
There you go. Congratulations.
Congratulations.
All right. Thank you for coming.
Thank you, folks.